So in this video, we're going to try and have a sense of what the electron configuration is based on the elements. So we're going to start with the first 15 elements, and we'll start to see a pattern, hopefully. So hydrogen, when you're looking at the number of electrons, hydrogen has one electron. That one electron will want to be in the first energy level in an S-shaped orbital, and there will be one of them. So a little bit about the notation. This number in front, the large number, the coefficient, tells you what energy level. This letter tells you what type of orbital, and this tells you the number of electrons that are in them. Helium has 2 electrons, and they still fit in that first energy level, but now there are 2 electrons. Lithium. Lithium has an atomic number of 3, which means its ground state electrons. There are 3 electrons. So the first 2 electrons will happily occupy the first energy level in an S-shaped orbital, and there will be 2 of them. But remember that the first energy level can only contain 2 electrons. So now that third electron will have to go to the next energy level, and it will want to occupy an S orbital rather than a P orbital, right? So 2s1. You'll notice that the superscripts, if I add them up, will equal the total number of electrons. Let's keep going. Beryllium has 4 electrons, so its electron configuration will be first 2 will go in the 1s orbital, and now I can fit 2 into the 2s orbital. Boron has 5 electrons. First 4 are going to be just like beryllium, but now it has an extra electron, and remember that that s orbital can only fit 2 electrons. There's only 1, so now it has to go into a p-shaped orbital, and there will be 1 electron. Carbon has 6 electrons, 1s2, 2s2, 2p2. Now it has 2 electrons in the p orbitals. We don't really know whether they're the x orbitals, the y orbitals, or the z orbitals. It really doesn't matter. We just know that they're in a p-shaped orbital. All the p orbitals within the second energy level have the same potential energy, so it doesn't really matter. Nitrogen has 7 electrons, 1s2, 2s2, 2p3. Oxygen has 8, 1s2, 2s2, 2p4. Fluorine has 9, 1s2, 2s2, 2p5. And neon has 10 electrons, 1s2, 2s2, 2p6. Now let's go on to sodium. Sodium has 11 electrons. The first 10 will be in the same way that neon is, so its first 10 electrons will be 1s2, 2s2, 2p6, but now the second energy level, remember, which can only contain 8 electrons, is full, both the first energy level and the second energy level. So now it has to go into the third energy level, and it will want to go into an S-shaped orbital. So its 11th electron, like the person taking the test, will be a 3s1. Magnesium is 12, 1s2, 2s2, 2p6, 3s2. Aluminum, 13, 1s2, 2s2, 2p6, 3s2. We can't have more than 2, so now I have to go to 3p1. Aluminum, silicon, 14, 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Sulfur, 16 electrons, 1s2, 2s2, 2p6, 3s2, 3p4. If this is starting to feel redundant, this is awesome because it means that you're starting to see the pattern. Chlorine has 17, 1s2, 2s2, 2p6, 3s2, 3p5, and argon, 18 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. Now is the time to start blowing your mind. All right, hydrogen and helium. So hydrogen and helium both have all of their electrons, the last electron, located in the first energy level. And if you look at your periodic table, hydrogen and helium are in the first row, and in fact, they are the only elements in that row. Lithium, beryllium, boron, all the way to neon, all of these 8 elements have their last electrons in the second energy level. Some in the S, some in the P. What do you see? Lithium all the way to neon are all in the, yes, second energy level, second row of your periodic table. Let's see if that holds true for sodium through argon. Sodium through argon have their last electrons in the third energy level. So one of the amazing things that you're realizing now is that for the periodic table, the row number corresponds to the highest energy level where electrons are located. Now let's see if we can figure out something about columns. Well, let's look at hydrogen, lithium, and sodium and see what their electron configurations are. Hydrogen, lithium, and sodium. Do you see it? Hydrogen, lithium, and sodium all have as their last electron configuration row number S1. What? Let's see if that holds true for beryllium and magnesium. Beryllium and magnesium, because there's no helium here, although we could put helium over there, they all end in row number S2. What? Oh my gosh, I have to jump all the way over here, but what do I notice? Everything from boron to neon are all in the P. And so is aluminum and argon have their last electrons in the p orbitals. Wait, this is called the p block. So now I can add something. I can say this is my s block elements. These are my p block elements. And what do I mean by p block elements? I mean that my last electrons are located in the p orbitals. Not only that, you'll notice that aluminum and boron are both 3p1. They're in the first column. Carbon and silicon are in the second column, and they are 3p2, but p2. So the column that they are in will tell you how many electrons are in that orbital. So the s orbital, all of these in the second column, have 2 electrons in their S-shaped orbital. Here, oxygen, 1, 2, 3, 4 columns into the p block, have 4 electrons in their p-shaped orbital. What? Let's see if we can figure this out. This block right here, from here to here, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What? Wait. Hey, what orbitals do we know can contain a maximum of 10 electrons? That's right, the d block. And then here at the bottom, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what does that leave us with? You got it, the F block elements. So the first designation of the periodic table that I can tell you is that the row number corresponds to the highest energy level where electrons are found. The columns will tell you what type of orbital they are in and how many electrons into that orbital they are. So if I pointed to selenium, you could say that its final electron is going to be the 4th energy level. It's in the p block, and it is 1, 2, 3, 4. So its last designation will be 4p4. Whoa, that's kind of crazy. Gets even crazier. you'll notice that potassium has 19 electrons, but it's in the fourth energy level and in the s block. So it tells me that instead of having its electron configuration, potassium as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, that this last electron seems to occur as the 4s1 electron. If we go back and we remember that as I start to cram more electrons into an energy level, even though they're the same distance away, the potential energy gets higher, we'll start to remember that, oh wow, these 10 electrons right here actually have a higher potential energy than the 2 electrons in the fourth energy level. So between our understanding of how even though electrons may be the same distance from the nucleus, the potential energies are different, and that these 10 electrons in the D-shaped orbitals of the third energy level are actually have a higher potential energy than the 4s electrons, it helps us understand what we already know from chemistry experiments already. The potassium behaves much more like sodium than it does a D block element. Remember that the periodic table, the way that it was organized, was done before electron configuration theory. In fact, Mendeleev didn't even know about the existence of subatomic particles. He simply made this periodic table based on 2 factors. One, increasing mass, and chemical reactivity. So all of the elements in one column are in the same column or a family because they behave the same way. One thing that electron configuration has shown us is that there's an underlying explanation that ties in the elements that are in a same family that also match our understanding of how charged particles behave. Like particles repel one another, electrons don't want to be too close to one another, and opposite charges will attract one another. And this helps us understand and predict the potential energy of electrons within an atom and how they will spontaneously arrange themselves in a way that maximizes the attractive force and minimizes the repulsive force on the group of electrons. Now remember, it's really important to know that I can't predict exactly where a single electron in potassium is going to be. I can just tell you the overall arrangement of the 19 electrons that will be there. And it's also important to remember that these electrons are in constant motion. It's just that within their motion, there is a method to the madness. So it's kind of like looking at a very complex musical number, right? Like Hamilton. So if you've seen Hamilton, they have some really complex musical numbers in which people are dancing, and it looks at first like everybody's just sort of like randomly moving around, and yet you know that in order for the actors not to bump one another, and in order to be able to predict where they're going to be, that each one has a prescribed place as to how they can move and how they can function within that overall set. Electrons are the same way. Even more so because they're moving around such high velocity. So hopefully this has given you some understanding and some sense as to how to start to see the electron configuration of this. And then the next video we will just practice doing this more and more in order to get this ingrained.